Hi, my name is Noah Arnold, and today I will be doing my Physics Lab 2, Lab 5 magnetic braking with Faraday. For the introduction, the purpose of this lab was to demonstrate Faraday's law by dropping a magnet into a tube of aluminum foil. The physics principles used were Faraday's law, the Biot-Savart law, Lenz's law, Newton's second and third law, and magnetic flux with a time derivative. The procedure of this lab included dropping a magnet into a tube and then time it by taking a video with your iPhone and do that 5 times. After you've done it 5 times, take the average and using the video and the average, perform the necessary calculations and go through the experiment using the code in GlowScript Python. To preview my results, my experimental time I found to be 1.25 seconds. That was the average. And then my computational time ended up being right around 1.2 seconds, slightly faster than the experimental time. Some basic data that I found before entering into Python GlowScript was that the length of my tube, my aluminum foil tube, was 0.3 meters, the width was 0.006 meters, the radius was 0.032 meters, the inner radius was 0.02 meters, the magnetic mass was 0.025 kilograms, and the time average that I found was 1.25 seconds. Before we continue, let me answer a few questions. Why can't we use a ferrous tube, for example, a steel pipe? This is too strong of a magnet and it might cause the magnet to stop entirely from falling rather than just slowing it down. What happens to the magnet? How does this compare to a magnet falling in free space without a tube? The magnet is moving in the tube and it falls slower in the tube than it would have fallen in open space. Here is some of my GlowScript Python code where I included all of the data that I recorded and then basically ran Faraday's law in order to see what was going on inside of the bar. On this slide, you can see the computational model and the results created by the GlowScript Python code. In the model, you can see two fields running in opposite directions. You can also see a velocity versus time graph. And then here you can see where it came back to be right around 1.2 seconds. Now we are going to interpret the simulation. The intensity of the coloring on the tube indicates the magnitude of current flowing through each ring. Red and blue indicate current flowing in opposite directions. Which color corresponds to clockwise current and which counterclockwise, and how can you know? So I used Lenz's law, and then using this law you can see that red is counterclockwise, leaving blue to be clockwise, which together work to slow down the magnet. What happens to the dynamics of the system when you flip the magnet around? So if you flip the magnet around, it would still not fall as fast as it would in an open space and likely at the same speed, but the currents would flip. The red and the blue that you see would flip. Interpreting the simulation part 2. How does the total time in tube of your real-world system compare to that of your computational system? And how might the computational system be made more accurate? The real world is slightly longer than the computational is, but that is likely due to air resistance, which is not accounted for, and if it were added, it would make the simulation more accurate. What does the shape of the velocity versus time plot tell you about the forces acting on the bar magnet? So as you can see, if we go back to the velocity versus time magnet, you can just see that it takes a little bit of time for the fluctuations to become balanced. And once those do become balanced, it remains basically constant throughout the fall. For the what if question, the resistivity of the conductor were reduced as close as possible to zero. How would the dynamics of the falling magnet change? The magnet would face a lot more resistance and could be stopped from falling from the tube completely. And then what if the holes or slots were cut into the tube? How would this affect the ring currents in your model? So the magnet would fall faster due to a decrease in current,